All right, we're going to call this our first example of an OR probability. We're going to show you how to compute the probability of one event or another event occurring. Okay, so in this example, we have a fair six-sided die that's colored in the following way. The faces 1 through 3 are colored red, the faces 4 and 5 are colored blue, and the face 6 is colored green. We want to find the probability that the face that we roll the die and the face comes up red or odd. Okay. Now, the fact that there's only 6 faces here actually makes this fairly easy. We can illustrate this pretty easily. We have 1, 2, 3 that are all red. We have 4 and 5 that are blue, and we have 6 that are green. Okay, so when we roll this die, there's 6 possible outcomes. Okay, in order to be considered a success here, we want to be red or odd. So I'm just going to make a little table here. And for each one of those, I'm going to ask, is it red or odd? Okay. The answer to the first 3 outcomes is definitely yes. Right? All three of those are red, so they're definitely red or odd. The blue 4 is not. It's neither red nor odd, so the answer would be no there. The 5 is odd, so the answer to that one would be yes. The green 6 is neither red nor odd, so the answer there would be no. Okay, so yeah, so this is a particularly easy one because there's only 6 possibilities, and out of those 6, 4 of them would be considered successes. 4 of them are either red or odd. Okay, so the answer, yeah, so the probability that it comes up red or odd equals 4 out of 6, which reduces to 2/3. Okay. All right, now, there's a common misconception here using math where you could say, the probability of red or odd, right? Because basically, in order to be considered red or odd, either one is okay, right? It could either be red or odd. So, a lot of times people think that this would just be the probability that it's red plus the probability that it's odd. Okay. But let's see. Let's see if if we do it like this, do we get the correct answer? So the probability that it's red, well, 3 of them are red, so the probability it's red is 3 out of 6. The probability that it comes up odd, well, let's see. 1, 3, and 5 are all odd, so there's 3 odd numbers. 3 out of the 6 numbers are odd, so that would be 3 out of 6. And if we did 3, 6 plus 3, 6, that'd be 6, 6, which is obviously not the correct answer because we already know that the correct answer is 2/3. It's not 6, 6. So something went wrong with our logic there. Okay, something went wrong. This formula for whatever reason does not work. Okay, and the reason it doesn't work is because when we do the probability of red plus the probability of odd, we're counting a couple of them twice. Okay, we're actually the 1 and the 3 are both odd and red, so it's like we counted them twice, which is why we got 6 out of 6 instead of the correct answer of 4 out of 6. So we need to adjust that formula a little bit. We need to make sure that we avoid double counting when we do these OR probabilities. And the way to do that is to subtract the probability that it's red and odd. Okay. And yeah, so notice what happens if we do this. then, probability of red is, 3 out of 6. Probability that is odd is 3 out of 6. Probability that red and odd, well, red and odd would be these two. So that'd be the 2 out of 6. And yeah, notice that if you do 3 plus 3 minus 2, that gives you the correct answer of 4 out of 6, which again reduces to 2/3. Okay, so what we've done is just, kind of by example there, we have derived a general formula. Okay, here is the general formula that works for any one of these OR probabilities, and here it is. The probability of A or B, it's going to be the probability of A plus the probability of B minus the probability of A and B. Okay, and that is a formula that you are going to want to memorize because you could use that formula for every single probability problem when they're asking you for the probability of one event or another event. And again, the biggest error I see is forgetting to subtract away this probability of A and B. And it's important to remember the reason that you're doing the subtraction. The reason that you're doing the subtraction is so that you don't count some of these outcomes twice. Okay, which is exactly what we would have done had we not done that subtraction with that particular example. Here's another example of an OR probability. We have a 20-sided fair die and a 10-sided fair die, and they're rolled. We want to find the probability of rolling exactly a 16 on the first die or an 8 or larger on the second die. Okay, so rolling two dice, each die is an independent event. And so what we'll do is we'll call rolling exactly a 16 on the first die. We'll call that event A, and rolling an 8 or larger on the second die, we'll call that event B. Okay, and we know that the formula for the probability of A or B, it's the probability of A plus the probability of B minus the probability of A and B. Okay, we got to remember to do that subtraction in order to avoid double counting the same events twice. Okay. Now, the probability of A is pretty easy. You got a 20-sided die, so each side is equally likely. What's the probability that you get that you happen to roll a 16 on that first die? That'd be 1 out of 20. Okay, because the 16 is 1 out of the 20 faces on that die. Okay, the probability of B getting 8 or larger on the second die. Okay, well, it's a 10-sided die, so 8 or larger would mean 8, 9, or 10. So that's 3, right? There's 3 faces that are 8 or larger on the die. So the probability of B would be 3 out of 10. Okay, now we need to subtract off the probability of A and B. And so here we have to remember a little bit back to a previous module. If you want to figure out the probability of A and B, which are independent events, the basic principle is you multiply the two probabilities. Okay, so the probability that we got exactly a 16 on the first die and 8 or larger on the second die, that'd be 1 out of 20 times 3 out of 10. Okay, so we have to do a little bit of we have to do a little bit of math here. We could easily just use a calculator, or we could do this by hand. notice, what, first of all, I guess when we do 1, 1 over 20 times 3 over 10, that'd be 3 over 200. Okay. And so in order to do the addition and subtraction, let's try to get a common denominator. 1 out of 20, if I want to make the denominator 200, I could just multiply top and bottom by 10. And then, the 3 out of 10, if I want to get the denominator to be a 200, I can multiply top and bottom by 20. And 20 times 3 would be 60. And so let's see, now the whole thing's just going to be some number of over 200, and 10 plus 60 is 70, minus 3 would be 67. So yeah, so the probability of getting, of getting exactly 16 on the first die or 8 or larger on the second die happens to be 67 out of 200. And it's a good thing we had the formula there, because when you roll a 20-sided die and a 10-sided die, there are 200 possible outcomes, and we wouldn't want to list them all out like we did, right? If there's only 6 outcomes, like the previous example, it's not too bad to just list them out. But if there's 200 possible outcomes, I certainly don't have the time or patience to list out 200 outcomes and then ask myself yes or no for each one of those. So yeah, so this is a really good example of where the formula saves us quite a bit of time. One more example of an OR probability here. Here we're given a table of some data of different colored cars that either did get a speeding ticket or did not get a speeding ticket. And what we want to do is if one person is randomly selected from this group, we want to find the probability that the person does not drive a red car or did not get a speeding ticket. Okay, so to try to organize this a little bit, does not drive a red car, let's call that event A. And then did not get a speeding ticket, we'll call that event B. Okay. And again, we know we're going to start off by writing the general formula that the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. And all 3 of these probabilities can be just read off the table. Okay. Let's see, first of all, if we want to find the probability of A, the probability that the person did not drive a red car, I'm going to look to this number right here. There are 522 in this sample that did not drive a red car. So this first probability is 522 out of 1029. Okay, there's 1,029 total people in this study here. Okay, so that's the first probability. Second probability, we want the probability that they did not get a speeding ticket. And let's see how many people did not get a speeding ticket. That number's right here. That's 941. Out of 1029. Okay. So there's our second probability here. And we do need to remember to do the subtraction here. We definitely have to subtract away the probability of A and B. We kind of know that right off the bat, right? Because if all you did was add these 2 probabilities together, 522 plus 941, it's, those 2 numbers right there are bigger than the total. Right? There's no way that our probability, there's no way that the numerator could be bigger than the total. Or, there's no way that the numerator can be bigger than the denominator. So, yeah, we definitely need to do some subtraction in order to make this make sense. So the probability of A and B, so, that's, we need to, we need to circle the number that tells us how many people both did not drive a red car and did not get a speeding ticket. And I believe that number is right here. Okay, 474 fit under both of those categories. So those, these 474 people, they were part of the 522. They were also part of the 941. So in order to avoid counting them twice, we will subtract. Okay, and so now all we got to do, right? When we add and subtract the fractions here, they're going to all have the same denominator. So all I have to do is 522 plus 941 minus 474, and that gives me 989.